Okay, good day. This is AP Calculus Summer Review. I am Mr. McCully, and this is SR7, Properties of Exponents and Logarithms. Trying to keep it a little shorter, so let's get right to it. Today we're going to be talking about performing operations on exponential functions, and we're going to work with properties of logarithms. These things are fairly easy, and we're going to get through them fairly quickly, but they are certainly properties that we're going to use over and over again in AP Calculus and things that you need to know cold pretty much going in. So just a quick review here, properties of exponents. If you have two exponential expressions that have the same base, when you multiply them together, you can just add. If you have a multiplication of two expressions to an exponent, you can take both of those two multiplied expressions to the exponent. If you have an exponent to an exponent, you multiply the exponents. Anything to the 0 power, as long as that thing is not 0, is always 1. And a to the negative x can be written as 1 over a to the positive x. If you have a division of two exponential expressions with the same base, you can subtract the exponents, and if you have a division of two expressions all to a certain power, you can separate it and take the top or the numerator to the exponent as well as the denominator to the exponent. So just some quick examples, and again, folks, this is review. This isn't supposed, I'm not really trying to teach you anything new. That you should already have a good grasp of these things. But if you don't, please again feel free to shoot me an email and I will try and help you through it. But just real quickly, I'm asking to simplify the following. And when we look at this thing, we can do this in a number of different ways. And that's what's so cool about all of these properties. As long as you apply them correctly, you can apply them in any order. They are in the, as far as order of operations goes, they are all in the level of exponents. So we could do this multiple different ways, and you may see it differently than I see it. And as long as you apply your rules correctly, you could do it in a different order and still get the right correct answer. So here's what I'm going to do. I look at this thing, and yeah, I could use this property here, this a to the negative x property, and make them all 1 over, oops, in the wrong one, all like this. I could make this one 1 over x to the fourth, but I don't have to do it that way. So here's what I'm going to do. I just know how to multiply fractions. When you multiply fractions, you multiply the numerators, you multiply the denominators. So I'm going to rewrite this first one as x to the negative fourth y to the negative second, just write it in alphabetical order. And then when I do the same thing on the bottom, I get x to the negative fourth y to the negative, ooh, that didn't like that. Let's see if we can't get rid of that. Okay, x to the negative fourth y to the negative second again. Well, if I look at that, I have the same thing on the top as I have on the bottom. And we know from fractions that that's just 1. But we could also use the other properties. We could say, all right, well, I've got an exponent over an exponent that have the same base, so I could subtract, and then I would get, let's see here, I would have x to the negative 4 minus negative 4. What the heck is going on with this thing today? I don't know why I'm getting this, but we'll try and muddle through. Minus 4, and then times y to the negative 4 minus negative 4. And when you go negative 4 minus 4, we would get x to the 0, and negative 4 minus negative 4, we would get y to the 0. And again, property of exponents. We have anything to the 0 power, as long as that thing is not 0, is 1. And so, what's the wrong screen again? I get 1 times 1, which is 1, equal to 1. Wow, what the heck is wrong with us today? I'm real sorry about that, folks. We'll try and... Okay, so multiple different ways to get that correct. Now, this one, second example. When you have a bunch of stuff going on inside an exponent, can we use the property of exponent and exponent and use the property of this expression here? We have multiple expressions on the inside, and you just take the exponent of all of those things. Absolutely, we could do that. But we could also simplify first. I notice I have an x in the top and an x in the bottom. And 2 minus 3 is -1, which would leave an x in the bottom. So I would have y to the 5th z over 2 to the x, and that I can just square. So y to the 5th squared, 5 times 2 is 10, so I'll have y to the 10. Z to the 1st times, or squared, would be z to the 1 times 2, which is z squared. Now the one that everybody forgets is this one right here. You still have to, still 2 to the 1st squared, and 2 to the 1 times 2 is 2, 2 squared is 4, and then again I've got an x to the 1st, so I've got x squared. So that'll be my final answer there. Final answer there, and let's move on. Okay, properties of logarithms. These properties right here, you learned back in Algebra 2 and we reviewed them in pre-calculus, and we said, well, why do we need to know those? Well, they're going to be very, very important in AP Calculus, and I told you that in Algebra 2, I told you in pre-calculus, and I'm telling you again today. These things are going to make doing derivatives later on a lot easier. And this expression, this is the one where we take the exponent and bring it down front. This is what we can use to solve exponential, or excuse me, solve equations that have variables as exponents. So we're going to do one of those later on too. Also, as a review, anytime you see just log with nothing underneath, we're going to call that log base 10. And anytime you see an ln, we're going to say that that is log base e, remembering e is Euler's number, which is 2.71, I think, 2.171, something like that. We don't have to memorize it. It's kind of like pi. All right, so let's look at this. We're going to expand the following. So here, if I look at this rule right here, if I have a multiplication of two expressions under a logarithm, I can expand that into a logarithm of the first expression plus the logarithm of the second. And so I'm going to do that right here, and I'm going to say that this is the ln of x squared plus the ln of y to the third. And I can further expand that by using this third property that allows me to bring the exponent down front and say that this is 2 ln x plus 3 ln y. All right, let's look at this one. This one is log base 10, and this one has some multiplication in the top and a division in the bottom. And so when you do have a division, if you have a logarithm of a division of two expressions, you can separate those two or expand those two into two separate logarithms with a subtraction in between. So here's what we're going to do. We're going to add the first two and subtract the last one in one step. So we're kind of combining properties here. So I'm going to say that this is log of x to the third plus the log of y minus the log of z squared. And then we're going to use that last property on the previous page to bring those two exponents down and say that our final solution for this, our fully expanded, will be 3 log base x plus a log base y minus 2 log base z. And those will be our two solutions here. Okay. Finally, we're going to reverse the process, and since it's a property, anytime you go from left to right, you can also go from right to left. So not only are we going to expand, but we're also going to condense. And before I can condense any of these, and if you notice in the properties here, there are no exponents here. So the only way I can do it is, or not exponents, there are no coefficients in front of either of these two logarithms. So before I can condense any of these two things, I have to use that last property right here, and I'm going to reverse it. Anytime I have that coefficient out in front of the logarithm, I'm going to push it up into the exponent. So when I look at this thing, the 2 has to go up, the 3 has to go up, the 4 has to go up. So I have log of x squared plus log of y to the third plus log of z to the fourth. Now, since they are all additions here, I can combine them with multiplications and say that this is the log of the quantity x squared y to the third z to the fourth. All right, similarly here with ln's, this ln does not have a coefficient, but the second one and the third one do. So I have to push the exponents up for both of those. So I'll have the ln of x plus the ln of x squared minus the ln of z to the third. Now, the first two I can combine with a multiplication. So I'll have the ln of x times x squared, and then I can condense this subtraction with a division, and I can say that is z to the third. And because x times x squared is x to the third, I can further condense this and say that my final answer is going to be the ln of x squared, excuse me, I screwed that up. I just told you that it is x times x squared, which would make it x to the third all over z to the third, and that is going to be condensed. All right, we are cranking through this. Just some real quick things to review. The interest formulas. You've got your simple interest, a equals p times 1 plus r to the t. Your compound interest function, a equals p times 1 plus r over n to the nt. And your continuous interest formula, a equals PE to the RT. Remember, A is going to be your final amount. Principal, P is usually principal. Did it again. I thought we were going good there for a while, folks. Or we could say initial amount. Your R is your rate as a decimal. So as a quick example, if they say 10%, then you're going to say R equals 0.1. N is your number of compounds. And as a quick example, if they say it's quarterly, I think I spelled quarterly right, we're going to say N equals 4, because there's 4 quarters in, I guess, in a year. T is your time unit. And a lot of times that's going to be years, but I say it's a time unit because you could do days, minutes, seconds, whatever you want it to be. Doesn't really matter. And E, again, is Euler's number. And that's located on your calculator. I'm going to show you that with my last example here. So real quick example for that, scientists testing the effectiveness of antibacterial soap on a culture of bacteria determines that there were 1 million bacteria at the start of the experiment, and there were only 1,000 bacteria left after 24 hours. What is the rate of decay per hour if the bacteria are decaying at a continuous rate? So as soon as we say it's continuous, we know that we're talking A equals PE to the RT. And since we're talking about decay, we know when you're decaying, R is going to be negative for decay, and R will be positive for growth. All right. So just kind of going through and labeling stuff. Since I have 1 million bacteria at the start, I'm assuming that that is my P, so we'll put that in there, 1 million. And there are only 1,000 left, so there's my final amount. 24 hours later, there's my time. So I've got, I need it to be 24. 24 at what rate? I'm looking for R. Check that out. I filled everything in. Okay, so let's solve this thing. The first thing I want to do to solve this is I'm going to want to take the natural logarithm of both sides, so I can use this property here to bring that exponential expression down in front. And you can see right here, I've got this exponential expression I'm trying to solve for r, so I need to be able to access that. But before I can do that, I need to get rid of this coefficient here, so I'm going to divide both sides by 1 million. And those cancel, and 3 of the zeros cancel there, so I have 1 over 1,000 equals e to the, and I'm going to change it around, multiplication is commutative, so I can do that. And then we're going to take the natural logarithm of both sides. And so I will have, you know what, let's just kind of scooch it over a little bit. I have the ln of 1 over 1,000 equals, bring the exponent down, so I have 24r ln e. And if you remember, ln, ooh, I didn't like that. Let's try one more. The ln of e is equal to 1. Oops, didn't want to go that far either. The ln of e is equal to 1. So this basically cancels out. It's just 1 times whatever. And so I'm going to divide both sides by 24, and so my final answer, the one that I'm going to put into my calculator, is going to be the ln of 1 over 1,000 divided by 24. So let's see what my calculator. I'll still have stuff from the last one. Okay, so quit out there. It's going to be the ln of 1 divided by 1,000. I don't have 1,000. Need 1. Close my parenthesis, divide by 24, and I should get negative. So negative, we'll say round to 3 places, so negative 0.228. So r equals negative 0.22. I don't think I said that. I said it wrong. It's negative 2.88. That is correct. It's equal to negative 0.288. There we go. Or a decay of 28.8% per hour. And that, my young Padawan learners, is the end. Only 17 minutes. And Star Wars fun facts of the day. Second Star Wars Force Awakens trailer. I say second twice. I don't know why I did that. Set a record for the most YouTube views in the first 24 hours. It was viewed over 30 million times. Well, that's all I got. You guys have a good day. Enjoy your summer. Bye.